Welcome to my 11th lecture on Fourier series and Fourier transform. In this video, we are going to discuss Fourier transform of periodic signals. And you see, in the previous lectures, we have discussed the Fourier transform of aperiodic time limited signal. So first, we will have a quick recap of that concept. Consider xt as a aperiodic time limited signal with time with capital T, suppose. Okay, and so if I consider one safe for that, and we will consider that this signal will start from 0 onward. So this is your one safe, and this is your capital T. So this is the periodic signal x of t. Now to get the frequency concept, so first of all we will start with periodic nature of this signal. So let us consider that this shape will repeat after certain time t naught, where t naught is more than capital T, means we'll insert one silent zone from capital T to t naught, and then it will repeat. This one, okay. So now this signal is becoming a periodic signal with time period t naught. So this time period is t naught. So angular frequency omega naught is 2 pi upon t naught, and that will be, if this is in second, then it is radian per second. Okay, so for this periodic signal we can have Fourier series expansion. Suppose this expansion is in terms of a complex exponential. So this is Cn times e to the power j n omega naught t, and n could be from minus infinity to plus infinity, all integers. And we can find the Cn values as 1 upon t naught times x of t multiplied by e to the power minus j n omega naught t. And it is for one time period, so let us consider it is from 0 to capital T naught. Okay, and this integral we can compute. So you can see this 1 upon t naught, as the signal is time limited, so this upper bound, so 0 to the upper bound is t only, we will go for up to t, and this is your xt, and it to the power minus j n omega naught t dt. Now this integration we can compute. Okay, so for that, suppose if I consider one function, this one, that x of t, okay, we'll consider this is your x of t e to the power minus j simple omega, a continuous variable, a dt. and this integration is 0 to capital T, and this function depends on only capital omega and the signal x of t. So it's a function of omega only, and that will consider capital X of j omega. If I consider this capital X of j omega is this much, integration of 0 to capital T x of t to the power minus j omega t, then this integral we can easily write it is 1 upon t naught times capital X of, so here omega is replaced by n omega naught, so j n omega naught, means this is the sample of this function x of j omega. Okay, so actual Cn, so what is happening? So we'll go to next slide. Cn is 1 upon t0 times capital X of j omega, where omega is replaced by n omega naught, right? So if we take one shape, so this is the shape for capital X of j omega versus omega. Okay, so you see these samples are like this one, these are the samples. So this is at omega 0 to omega 0, like that it is in omega 0. Similarly for left hand side, and actual Cn is 1 upon t naught times of these samples. Now if t naught is increasing, so if we increase the t naught value, means the signal will repeat after a long time. So if I consider that t naught is more, so in that case the spectrum, the actual Cn, okay, so I want to get the Cn value. So this envelope is now reduced by this factor 1 upon t naught. Okay, so it will be like this. Because of this t naught, 1 upon t naught, and then we'll have the samples, and as t naught is more, omega naught is less, reduced. It implies that omega naught will come closer to the origin. Okay, so all the samples are closer to each other, right? Both sides. And you see the magnitude of Cn, this is also reducing. Okay, and when t naught is infinite, is approaching to infinity, then we can assume that the signal xt becomes practically aperiodic. As the signal shape will repeat after infinite times, and that time the true Cn value, you see, is approaching to 0. Okay, because of this factor 1 upon t naught. So this if all the samples are becoming close to 0, then we can't get any spectrum, significant spectrum. So to get one significant shape, spectrum shape, we'll exclude this 1 upon T naught and we'll consider only x of j omega. It's implied that we are going to take Cn times T naught, this product, sorry, Cn times T naught, and that is your x of j omega, and this is the Fourier transform we will consider for the signal x of t. And this spectrum, you will show what you see, this xt signal will have a Fourier transform, that is capital X of j omega, and for aperiodic this capital X of j omega becomes continuous, okay, and the true Cn value is approaching to 0. So we have amplified the actual Cn value by infinite times. So this one we have got x of j omega, just amplifying actual Cn by infinite times. So this concept is useful to understand the Fourier transform of periodic signals, because we have to maintain some uniformity in Fourier transform. So you see, in a periodic signal, the spectrum is actually the infinite times of actual values for Cn. So this is amplified by infinite times. Now, in contrast to this aperiodic signal, we will consider a periodic one. Let us see. So for periodic signal, you see the Cn is significantly high for some values of n. Right? So this is a true Cn value. So here also, to get the spectrum, so you see the spectrum x of j omega, it should be a infinite time amplified version of the Cn. So Cn is already significantly high. So if I multiply with infinity, then its value will become infinite, either positive infinity or negative infinity. Right? So what we can say, that x of j omega will contain infinite samples, and again here T naught for this periodic signal is finite. Thus omega naught is 2 pi upon T naught. It is also finite, it is more than 0. So you will have some discrete spectrum, and those points omega naught, 2 omega naught, 3 omega naught, n omega naught, there the spectrum values will become infinite. So here it should have discrete spectrum, and magnitude at n omega naught, or omega equals to n omega naught, is infinite. It should be infinite. Okay, that implies that this x of j omega should contain a del function. Okay, because del function will have infinite amplitude and it will be located at n omega naught. So it should be of this form, del of omega minus n omega naught. Okay, that is the main idea of periodic signal. Now we'll take few examples, then we'll consider any aperiodic signal, what is the spectrum. The first one, we'll consider that suppose one spectrum x of j omega is simply 2 pi times del of omega. So it will contain one impulse. Okay, so what is the corresponding time signal x of t? So to obtain this x of t, we should use inverse Fourier transform. So if I use inverse Fourier transform, okay, so xt is given by 1 upon 2 pi times capital X of j omega times e to the power, this is j omega t and dt. Right? It is integrated, sorry, one it is with respect to omega, d omega. Now for this signal, you see it is 1 upon 2 pi, and now this x of j omega is given by 2 pi times del of omega. Okay, and this is your e to the power j omega t d omega. So these 2 pi will cancel. That's how we have included this 2 pi to get the cancellation of this 2 pi. Next, so this becomes simply del of omega times, this is your e to the power j omega t and d omega. So you know that whenever a del function is multiplied with any function, because this function will exist at omega equal to 0 only, so we can put omega equal to 0 in this function, because omega not equal to 0 every time this value is 0, so there is no meaning to consider this signal. Okay, so the principle is that this one, any del of omega and f of omega, that we can write del of omega times f of 0 only, because it will exist at 0 only, so that we can replace. Okay, so what you will get, so this is del of omega and this value is e to the power 0 is 1 and it is d omega. An area under the impulse signal is considered as 1 because it is a unit impulse. So x of t is 1. So what is the meaning? Meaning is that the inputs, sorry, time domain signal is constant at 1. The time axis, this is your xt, and corresponding spectrum is the omega. You are having one impulse that is located at 0 only. Okay. Okay, and this one is 2 pi del omega. That is your x of j omega. So one conclusion is that this time is now, it's not a time limited signal, it is time unlimited signal. It is constant for all time. So it will give you one DC value. For DC value, you will have a zero frequency. So omega will be 0, it will exist only, and its value is 2 pi del omega. In a similar way, if we consider x of j omega is having a spike at omega equal to omega naught, suppose. Okay, so 2 pi del of omega minus omega naught. Okay, so you see, if you use inverse Fourier transform IFT, so x of t would be 1 upon 2 pi times, and this is the x of j omega, that you can put it here, 2 pi del of omega minus omega naught, then e to the power j omega t and d omega. You will see this will cancel, and now this function will exist at omega to omega naught, and then the area under this curve will become 1. So eventually you will get e to the power j omega naught t. So it implies e to the power j omega naught t will have a spectrum of this kind, 2 pi times del omega minus omega naught, a single frequency. So the spectrum is like this. At omega equal to omega naught here, you are having a spike, infinite one, and this is 2 pi times del omega minus omega naught. So it's single frequency. So similarly, you will get e to the power minus j omega naught t. Its spectrum should be 2 pi times del of omega plus omega naught, the left hand side. Okay, so in this way we can find now the other signals. So we have considered this one a periodic signal, complex periodic signal. This is another complex periodic signal. Okay, now we can consider some periodic real signals. Before that, we'll be using one property of the Fourier transform that is called linearity. Okay, so linearity property of Fourier transform. What is this? If we have a signal x1t and its Fourier transform is capital X1 of j omega, and for x2t its Fourier transform is suppose capital X2 of j omega, then the Fourier transform of a composite signal, suppose a x1t plus b x2t, it will have, you see what I can do. So this Fourier transform, by definition, what I can do, so this is a signal a x1t plus b x2t. We have to multiply with e to the power minus j omega t, and we have to integrate. Now this integration operator is a linear operator, so we can break. So we can have this one, a times x1t e to the power minus j omega t dt, this one, plus b times again we will have x2t e to the power minus j omega t dt. So you see the first one we can write as a times capital X1 of j omega, that this is the Fourier transform of x1t, and second one is b times capital X2 of j omega. So Fourier transform of this composite signal is now same coefficient a and corresponding spectrum we will multiply and then we'll add. So this is the linearity property and we can use it to find Fourier transform of other periodic signals. Now see. Now fifth one, if I consider xt is a cos waveform, cos omega naught t, and that we can write half e to the power j omega naught t plus half e to the power minus j omega naught t. So therefore, using linearity property, the capital X of j omega will be simply this half times. Now Fourier transform of this one already you have seen, it is 2 pi times del of omega minus omega naught, and this is half again 2 pi times del omega plus omega naught. So it simply 2 will cancel out, one is pi and then one del function here, another component here pi, and del function at omega equals to minus omega naught. So spectrum, so this cos waveform, okay, this amplitude is 1, this is a cos omega naught t, this is your t naught, then you will have a spectrum like this at omega naught, omega equal to omega naught, this is your omega, you will have a spike here, impulse here, and another one omega equal to minus omega naught, you will have another impulse, and the strength we will call it pi del omega minus omega naught, and this is your pi del omega plus omega naught. So in the same way, if xt is sine 1, sine omega naught t, and you see this one we can rewrite as half or 1 upon 2j e to the power j omega naught t minus 1 upon 2j e to the power minus j omega naught t. So you will see capital X of j omega will have two components, 1 upon 2j times 2 pi del omega minus omega naught minus 1 upon 2j times 2 pi del omega plus omega naught. So 2 will cancel out. So you are getting 1 upon or pi upon j del function omega minus omega naught minus pi upon j del omega plus omega naught. So again you will have two, one is here and another one is negative, so I can put it here this side, okay, but again it is single frequency at omega equal to omega naught, and negative corresponding negative frequency is omega minus omega naught. Okay, now if I consider any periodic signal, xt is a periodic signal with time period t naught second, that imply the fundamental frequency, the angular frequency is 2 pi upon t naught radian per second, and we can express this xt in terms of sinusoidals using Fourier concept, Fourier series concept. So if I use Fourier series, then xt can be written as the summation of Cn times e to the power j n omega naught t, okay, and n is minus infinity to infinity. Okay, so you see, if this is signal, so easily we can say that spectrum x of j omega will be, so now we can use linearity property, and Cn is a constant, so it will remain summation n equals to minus infinity to infinity, and this Cn remain constant, and for this exponential will have a spectrum of 2 pi times del omega minus n omega naught. Okay, so actually it is 2 pi, outside I can take, it is Cn, it's a delta omega minus n omega naught, n is minus infinity to infinity. So if you have Cn like this, so these are the actual Cn. Okay, this is at omega naught, 2 omega naught, like that, omega. For this periodic signal, then x of j omega the Fourier transform will be similar, but will have a spike here. Okay, impulse. We'll consider a impulse here. Next impulse will be here. Next one is here. So discrete impulses will get like this, and those values will put 2 pi times of that values. So these are 0 at omega 0, it's minus omega 0, like that. So you'll have a discrete spectrum and containing all the impulse signals. Okay, so this is the main difference from a aperiodic signal, the Fourier transform of aperiodic signal and Fourier transform of periodic signal. So the conclusion is that for time unlimited periodic signals, we should have a impulse function in spectrum. In other words, if the spectrum contains one impulse, then obviously that is corresponding to one time unlimited signals. It could be a DC or could be a single AC component. Okay. Okay, we will continue the discussion on the Fourier transform. We will discuss the properties of Fourier transform in the next videos. Please keep watching my videos and subscribe to my channel to get all the upcoming videos. Thank you.